We left off here. We were talking about, we have been talking about bonding, hybridization, all that stuff. And now we're going to extend that to structures and how certain structures are depicted. So we talked about condensed forms, right? Where we said that you would take the groups that are identical, group them up where possible, and put them in parentheses with subscripts. And then the subscripts indicate how many of each group is there. We talked about that. And then we took that and expanded it out to the Lewis form, where you draw all the carbons, all the hydrogens, all the bonds, show everything. All right. And then from that, we picked out the longest chain, which is the parent. And based on the parent, that parent is going to tell me what the skeletal form looks like, which is here, right? Where you just show the vertices and the termini. And remember that every terminus is a CH3. So the end of every line, same will be for here and here, but you don't have to show them because it's a skeletal form, right? And everywhere two lines come together, unless there's some other atom there, it's understood that it's a CH2. So these are they're two hydrogens on each one of these carbons here. Right, so that would be the skeletal form for this molecule, and we can name it. I haven't taught nomenclature yet, but I always like to throw it in when it's appropriate, right? So if a CH3 like this is hanging off of a backbone, then we call it a substituent. Right, and that substituent is based on what it is, that's how we name it. So in this case, a CH3, if you watch that video I sent you, then you kind of already know where I'm going. This is what we call a methyl group, and it's derived from CH4, which is, sorry about that. Methane. But then when we take one of the hydrogens and pull it off and attach that methane to something, we change the ending. So when we attach it to something else, it's called a methyl. Right? So here we have two methyls on this chain. We have one on one end, one on the other end. And so we can actually name this real quick, but we have to, again, that's why finding that longest chain, that parent, is so important. But we can go in and we can number it. It doesn't matter which end you number from in this case, because the two methyl groups are equidistant from the end, so it doesn't matter. So we're going to number from here. One, let me pick a different color. So this is 1, 2, 3, 4, 5, 6. What is 6 carbons? What's the parent name for that? Anybody? You watched that video I sent you on Wednesday, then you should know that.
Hexane.
Hexane, excellent. Who was that?
Michael.
Thank you, Michael. Hexane is my parent. So anytime you name a compound, the parent always comes last, right? And then we have methyl groups located at position 2 and 5, right? So anytime you have identical groups on different carbons, you have to list them together with a prefix, right? So this is going to be 2, 5, that's the address. And then because there are 2 of them, we'll say dimethyl hexane, right? That's the name of that compound, 2,5-dimethylhexane. Again, the 2,5 is that anytime you name a compound, you always have to give, and I like to think of it like a street. So you have a address, and you have your residence, and then you have the street name. It's just an easy way to think about it. And then if the residents are the same, then you have to indicate that. So this will tell you the number of residents if you have identical substituents. All right, I'm not going to dive too much deeper into nomenclature because we got a whole set. We're going to do a whole section on it, but I always like to introduce it when the time is appropriate. So let's do another example. It says convert each molecule into a skeletal structure. Which one do you want to do? Y'all pick one. Somebody pick one. So we've done A. We're going to do 3 of them. Anybody? We definitely want to do one of the rings. Did you say D or B?
Yes, I did. I said D.
D. Okay.
And
then we're also going to do B because B introduces us to some other functional groups that we get a chance to talk about, which I love being able to teach 10 different things from one example, right? That makes it easier for you on the receiving end, and it makes it easier for me to be able to hit different concepts using one example. Instead of showing you 59,000 examples and each one is something different, we can talk about one example and do multiple ideas from that. So let's start out with D because D is going to be the easiest of all of these, right? Notice in D, right, I'm just going to move this. I'm going to draw it over here. How many carbons are in that ring? Notice it's a ring, so we don't have to worry about finding a parent. The parent is the ring. It's six members, right? You got 5 carbons and a nitrogen. So if you were to draw that in skeletal form, right, you would draw it out, draw out a hexagon, which is a 6. That's our description or illustration of a 6 atom unit. That's cyclic, right? We're going to call this, anytime you hear me use the term cyclic, that means I'm talking about something that's a ring. You can have 3-membered rings, 4-membered rings, 5-membered rings, 6-membered rings. I mean, there are a lot of different sizes of rings that can be formed. That's the beauty of organic. These atoms can do pretty much whatever they want to do. All right. Now, what am I missing inside the ring that I have drawn? Look at the structure up here, right? Let's start at the nitrogen. We're going to put that in here. All right, I'm gonna put that nitrogen in there. What else do I need to put in? Look at the ring and tell me what I need to add.
The double bonds.
The double bonds. Good, excellent. I need to add in my double bonds to this ring, right? So I'm going to put them in just like I see them up top. I'm going to put one here. I'm going to put one here, and I'm going to put one here, and I'm going to put that lone pair back on nitrogen. And that's it, right? All I did was draw out a hexagon, and every vertex in that hexagon is a carbon or nitrogen. In this case, you have 1 nitrogen and 5 carbons. And then if you notice up here, right, even if I don't have the hydrogen shown, they're understood to be there. Why? Why can I make the assumption that there's a hydrogen present on an atom, on a carbon? Like what's missing from that carbon that tells me that there has to be a hydrogen there? Anybody? Is it charged or is it neutral?
It's neutral.
Neutral. So what does that say? That says that it has to have 4 bonds to it. And if you count up the number of bonds, right, to any one of these carbons, it's going to be 4, right? You got a double bond here. Let's say for this carbon, you got a double bond, that's 2, that's 3, and that's 4. right? So I don't have to show those hydrogens, they're understood to be there. All right. Oh, I see. Now, how do I pronounce that? Is it Wichelle? Is that right?
Yes.
Okay, good. I didn't mess that up. Yeah, you're right. The lone pairs were missing. I just looked at the chat. But thank you for that. All right. Any questions about that one? Cyclic structures are always easier to deal with because you don't have to worry about the parent. The ring itself is the parent, so you don't have to worry about it. This particular compound is a compound known as pyridine. Right? It's ubiquitous in organic. You can use it as a base. It's a very good base, as a matter of fact, and it's not overly, how do I put this? Not overly caustic. It's not a super strong base, but for the most part, it's used as a base when you converting alcohols into other functional groups. All right, we said we're going to do B, so let me copy that because we're going to need some room for that one. Actually, you know what? Can we do E right quick? Let's see if we can figure that one out. What do I need to draw first for E? What would you do first?
The cyclic ring.
Draw the ring. You know that's your parent. Everything else is going to be connected to it. Is that right? And so let me draw it in the same. Without rotating it. All right. So then we had a double bond here. Is that right? And then attached to that double bond, we have a CH3 group. We're just going to draw that out here. We don't have to actually write out the CH3. We don't want to. And then what about on the other carbon over here? How would you draw that double bond? Is that right? This is a great example too, because I get to talk about this. Why? Okay, so let's look at the double bond itself. Why is this carbon a CH2? Help me out.
Because it's a double bond there.
Yeah, the double bond itself, right? So the end of that double bond, that carbon, if it's not charged, then it has to have 4 bonds to it. So the other two bonds are understood to be hydrogen. Very good, right? So anytime you see a double bond written out, sometimes you'll see it written like this, right? With no demarcations, no atoms shown. It's understood that that end of that double bond is a CH2. Right? The double bond itself belongs to a class of compounds. Right? There are 2 double bonds in here actually. When we have a compound, a double bond present, we call those alkenes. ALKENES. And the enes on the end tells me that there's a double bond present. Right. So the ene part tells me that there's a double bond present. So anytime, and I'm introducing that, even though we'll start on functional groups next week, I'm introducing that now because you can never learn functional groups early enough. So when double bonds are present, that's called an alkene. All right, let's go back to, what did we say? B. We just skipped all around everything. But let's do B. B is asking us for, it says draw the skeletal form, but first, I really would prefer to do the Lewis form first and then explain the parentheses and all this stuff. So when you see in a condensed form, right? You see in the condensed form, an atom in parentheses, that atom is bonded to the atom to the left of it. Same with the OH. When you see the OH in parentheses, it's actually bonded to the atom to the left of it. That's really matters, right? Because if you try to put it on this atom, that's not going to fly, because when we draw this out, you're going to see that that atom will have 5 bonds to it if you try to do that. And that's not going to fly. All right. It will be the same if you tried to put the chlorine on the atom to the right. So let's draw it out. So we got, let me see, 1, 2, 3, 4 carbons. So let's draw that out. Carbon. And then on the ends, we have CH3s. Right. The second carbon is a CH. And then I'm going to put that chlorine on it. And then the third carbon is a CH. I'm going to put the H down here. I'm going to put the OH there. Do you see what I mean? If I had tried to put the OH on this side, that carbon will have 5 bonds to it. And carbon can't make 5 bonds ever. Whatever you do on the exam, never put carbon with 5 bonds to it. I'm going to call you. I'm going to find your number and call you. And I won't curse, but you'll know I'm upset. Carbon can't make 5 bonds. So it can make 4 bonds, it can make 3 bonds, but it will never make 5 bonds. All right. So that's why I'm saying the OH is bonded to the atom to the left. So when it's in parentheses like that, it's bonded to the atom to its left. All right. Questions about that? Now, what would the skeletal form for that look like? It's 4 carbons. Go ahead. Come on.
On the second carbon, like, would it matter if you put the
Put it up or down?
chlorine on the top or the bottom?
Nope, it won't matter. I just did that because in my mind, I know that when you put 2 big atoms together on the same face, then that's bad. It's called steric hindrance. And so that's why I just drew. It's just a default mechanism in my brain to not put those 2 next to each other. But for the purposes and the scope of what we're talking about, it wouldn't matter. All right. Any other questions? So now we need to draw, this is Lewis. Now we need to draw the skeletal form. Is that right? Well, I'm actually going to use this example to talk about something else too. So what does the skeletal form look like? How many carbons?
4.
4 carbons. So that's going to mean 3 strokes. Sorry. All right, so that's your 4 carbons. Where is the chlorine and where's the OH?
The chlorine's on the second carbon and the OH is on the third.
So we'll do that and we'll do that. Okay, good. So this is the Lewis, this is the skeletal form. All right, this is an example of, so where you have your chlorine, right? This belongs to a class of atoms. You'll probably already know this, called halogens, right? If you have an OH attached to your backbone, this compound is what we call an alcohol. Normally with OH, if it's just by itself, it's a hydroxide. But when it's bonded to carbon, that functional group becomes an alcohol. All right. So anytime you see an OH bonded to a carbon in a chain or in a ring, it doesn't matter. It's going to be classified as alcohol. All right. Any other questions about this, about skeletal and line? I want you to try this one on your own. If you get stuck, you can bring it up on Wednesday. What's the date? It's the 2nd. Right? Questions about that, about anything? All right. So when we think about skeletal line forms, we can just, if we start out with the condensed or the line, we should be able to interconvert between the line and the condensed and the skeletal. All right, let's do, I need to grab a extension cord. Give me 1 second. Let me grab a extension cord so I can plug up my iPad. One second. I'll try to chop this part out of this video before I post it. All right, let's work through a few of these formal charge problems, and then we're going to talk about polar, covalent, non-polar covalent bonds and dipoles. All right. Let's go here. I'm gonna pick out a few. A, F. We'll do G, and let's do H. Actually, and E. That's more than a few, but we need to practice. All right. So remember the other day we talked about formal charge. How do we determine that? What was the little formula I gave you?
I got that formal charge is equal to the number of valence electrons minus the actual number of electrons, which
Valence.
include lone. Oh,
Go ahead.
So valence electrons minus actual electrons, which the actual is the number of lone pairs plus half of each bond.
Good. This is not good. So valence minus actual. Come on, iPad. All right, no mind. More than one way to skin a cat. Minus actual. I think the touch part is acting stupid because I got it plugged up. All right. That's okay. We're gonna work it. So valence minus actual is the formal charge. All right, so let's look at A. We're going to do the formal charge for aluminum. All right, aluminum is on the periodic table. Somebody tell me what the valence is for aluminum. Based on where it is on the periodic table. Is it group 3, group 4, group 5, group 6, group 1, group 2? Where is it?
3.
Group 3. So how many valence electrons should it have?
3.
3. So the formal charge here is going to be what? 3 minus what? How many are around it? What's the actual? Got 4 bonds around it. Is that right? So the actual is going to be 4. Yes. So the formal charge for aluminum in this case is going to be -1. Questions about that?
Where did you get the 3 from again?
That's the valence electrons. So the valence is the group number. You can determine the number of valence electrons by what group the atom is in. So aluminum is in group 3. So that means it has 3 valence electrons. Right, if you look at the periodic table, you go from group 1, group 2, then you got the transition metals, and then group 3, group 4, group 5, group 6, and group 7, or group 7 and group 8. Group 8 noble gases, group 7 are the halogens, group 6 is oxygen, 5 is nitrogen, 4 is carbon, 3 is boron, and then followed by aluminum. All right, let's do F. What's the valence for carbon?
It's 4.
Mhm. So this one is going to be what? 4 minus what? How many around it?
3.
3. Good. You got 3 electrons around it. So 4 minus 3 is going to be +1. Right, so that carbon is going to have a positive charge. All right, questions? Is everybody okay with that? I'm pushing through this quickly because this is a concept that we can, if you know how to count the electrons, then you're good. All right. All right, somebody do G. Let's do oxygen in G. Because carbon is going to be neutral, right? You can see that both of those carbons have 4 bonds to them. So the formal charge is going to be 0 for both. What about oxygen? What do we got? What's the valence? How many valence electrons does oxygen have according to the periodic table?
6.
6.
Mhm. Good. And then how many are around it? You got a long pair.
5.
Did you say 5?
Mm-hmm.
Excellent. Long pair, and then 3 bonds from that triple bond. So 3 electrons from there. So that's 5. So that charge on oxygen is going to be +1. And I can write that here. I don't have to put a number. I can just put a positive sign over the oxygen and say that it's +1. All right. Without calculating, what is the formal charge for aluminum here?
-1.
-1. We just calculated that on the other side, right? It's got 4 things around it. Aluminum is a group 3 element. If it's got 4 things around it, then it's by default, it's going to have a formal charge of -1. All right. All your chlorines are good. Well, not all of them, but the terminal chlorines are good, right? They all have 7 valence electrons. They all got 7 around them. So the formal charge is going to be 0 for those. But what about this one? Let's calculate that. So for chlorine, it is, the valence is 7. Is that right?
Yes.
So valence is 7. Actual is, let's count them up, 2 long pairs. and then 1 from each bond. So that's a total of what?
Six.
Total of 6. So the formal charge on chlorine is going to be +1. But this is a good example. What's the overall charge on that molecule? If the aluminum is -1 and the chlorine is +1, what's the overall formal charge?
It's neutral.
Neutral. Good. Excellent. Overall charge is 0 because the charges are going to cancel out. Just going to highlight this. So those charges will cancel. All right. All right, everybody okay? And let me know if it's going over your head, if you missed something, if I missed something, speak up. All right, let's do E. Somebody do E for me. You can feel free to annotate the screen if you want. Just click on the toolbar for Zoom and click the pencil that says annotate.
Wouldn't it be a formal charge of -1?
-1. Good. I agree. How did you calculate that? How did you come to that determination?
Because carbon has a valence of 4, and then there's 5 electrons
Good.
to the central atom. So
4 minus 5 is going to be -1. That's exactly right. Who was that?
Kadir.
Yeah. Nice work. Nice work. Nice work. That's exactly right. So the valence is 4. The actual is 5 because of the lone pair and 1 from each bond. So the overall formal charge is going to be -1. Excellent. All right. Let's go to here. But I want to bring, I want to add a page because I want to talk to you first about bonds and polar covalent bonds and non-polar covalent. I think I mentioned it in one of the lectures, but I want to talk in more detail about it here. So I'm gonna grab this example that we did up here. Yeah, this one. Perfect. All right, let's do that. So in this section, we're going to talk about, let me just say covalent bonds. Why the screen is doing this? I really need to get a new iPad, but I want to drop the coins. All right, so we're going to talk about covalent bonds. Save that. And basically, you have 2 types. I think I mentioned this before. But first, let's talk about what the term covalent means. All right, so we have a covalent. Come on, iPad, before I smack you. All right, let me try this again. I'll just write the example out when it's time. So the term covalent, I'm going to underline the prefix co. That's the term we use to talk about a bond that's made by sharing electrons. You probably heard this in GChem. And before you panic, when I say electrons, I'm abbreviating that with E minus, so shared electrons. That's what covalent means, right? We talked about this before. Like, let's talk about it from the valence perspective, right? So valence, when I say sharing electrons, these are valence electrons. Right, and if you remember when we talked about hybridization and orbital overlap and all of that, so the way that valence electrons are shared is through that type of orbital overlap. So let's take a basic example, like if you have a hydrogen atom with one electron, and you have another hydrogen atom with one electron, and you add them together, that's going to be constructive overlap. So the two orbitals are going to add, and then the electrons are going to be here, right? So there's going to be a hydrogen here and a hydrogen here, right? So in order to add these together, we got to overlap those orbitals. Right, so when you add them, that additive effect is shown here, where you have, instead of two hydrogen atoms in separate s orbitals, you add them together and you get a new orbital. All right, so this bond between those two hydrogens is what we call covalent, right? The cold part again is shared. The valence outer shells are shared, so we call it covalent. This is an example of what we call a non-polar, I think I told you this before, but it bears repeating, non-polar covalent bond. Right? The way you determine whether something is non-polar, whether a bond is a non-polar covalent bond, is by the difference in electronegativity. How many of you remember what electronegativity is and what it measures? Anybody?
It's like the ability for one atom to like attract more electrons than another, or like unequal sharing of electrons in a molecule.
Okay, good. That's exactly right. So when you talk about electronegativity, what you're talking about is an atom's ability to polarize a bond, right? And so when you have two atoms together in a covalent bond, that those two atoms, if they have and there's a scale we're going to use, if they have an electronegativity difference that's small, then we consider it nonpolar, right? Or neutral in this case, because both atoms are the same, we consider that nonpolar. If you have a difference that's big, then there's another kind of bond, and we call it a polar covalent bond. So let me draw that molecule back that we had, and we're going to use this to illustrate it's a chlorine here, I think. A non-polar covalent bond or a polar covalent bond. And I'm actually let's draw. I want to draw this out because there's a bunch of stuff I got to talk about. All right. So when we look at, let's just examine this bond right here, the carbon-oxygen bond. Right. We know it's covalent. What orbitals are overlapping to make that? Let me put the lone pairs in on oxygen. Now this we talked about already. So what orbitals are overlapping to make the carbon oxygen bond? Okay, let me back up. What's the hybridization state of carbon?
SP3,
It's sp3. What about oxygen?
SP3.
It's also sp3. So you have sp3, sp3 overlap making that bond. The question is the bond, we know it's covalent because those orbitals overlap and share a pair of electrons. But the question is it non-polar or polar, right? So if we were to draw this out, I'll just draw it out like this. So you have your carbon with an sp3 hybrid, and that's going to overlap with oxygen that has an sp3 hybrid. It's got lone pairs and a bond to hydrogen here. So we're going to overlap these two orbitals, right? And then it's going to be, of course, it's going to be additive. So it's going to be, instead of two hybrids, now you've added those together. And this still has its lone pairs and the bond to hydrogen. All right, don't worry about that part. And then, of course, this has three other bonds to it that I'm not going to show. All right, so when those two add together and share electrons, the question now is, which direction are those electrons going? Are they going towards oxygen or are they favored towards carbon? That's how we know if something is polar or non-polar. So the way we tell the difference is to look at the two atoms, which in this case is carbon and oxygen, and we find the difference in their electronegativities. So for oxygen, I know oxygen by heart is 3.5 because it's the second most electronegative atom on the periodic table. What about carbon? Can somebody look that up real quick? What the electronegativity is for carbon? I think it's 2 point something.
.55.
Okay, so 2.55. All right, I'm gonna round that up. Since the other one is 2 sig figs, I'll round it up. What's the difference? It's 0.9, is that right? Right, so that difference is on a scale. We have a scale that we can use to determine if it's polar covalent or non-polar covalent. So if the difference in electronegativity, depending on what book you have or what source you use, the scale actually is a little bit different. Some scales stop at 0.3 for non-polar, some stop at 0.5. If I'm not mistaken, the Klein book is at 0.5, so that's what we're going to use. All right, so if the difference in electronegativity is less than or equal to 0.5, then it's non-polar. If the difference in electronegativity is greater than 0.5, then we say it's polar covalent. Right? And then you have another type of attraction. It's not really a bond, it's called ionic. And if I'm not mistaken, that's greater than or equal to 1.5. All right. So here, the difference in electronegativity is 0.9. So is this a polar covalent bond or a non-polar covalent bond? Anybody? If the difference in electronegativity
Polar.
is polar, right? It's greater, the 0.9 is greater than 0.5. So that's how we determine that. If we have we know the electronegativities, we can look on the periodic table or we can Google them, right? But now we know that this is a polar covalent bond, right? So what that means is that the electrons that are shared are closer to the more electronegative atom. So the electrons are unequally shared. One second. So the electrons are unequally shared and they're favored toward the more electronegative atom. All right. So for that polar covalent bond, those electrons are going to be shifted more towards oxygen. Are y'all following that? Because the more electronegative an atom is, the more it's able to polarize a bond, the more it's able to pull electrons towards itself. All right. And we indicate that. I mean, the last thing I'm gonna say, and I'm stopping here. We can indicate that by showing what's called a dipole arrow. Right. So I'm gonna, for this bond, the electrons are going towards oxygen. And so I put in a dipole arrow to show, excuse me, to show that. So this is what we call a dipole arrow. So every polar covalent bond is going to have a dipole, an individual dipole. At the end of this arrow where the electrons are going, that is, we say that it is partially negative because those electrons have a negative charge and they're going to be concentrated on one side. And on the other end, we say that that atom, that carbon is partially positive. This is very important because this is going to dictate how certain molecules and certain functional groups react based on their polarity. All right, we got to stop. I'm 2 minutes over. Any questions? All right, no questions. All right, go enjoy your weekend.